We continue our lectures about random operators, strong random operators, and about application of strong random operator to random elements in Hilbert space. Last time we discussed a special case of random operator, namely strong Gaussian random operator. Let me recall you, what is it? So we have Hilbert space, which is real and separate. And we have the linear operator A, which acts from H to L0 omega pH, and is linear and continuous in probability. This is a strong random operator in H, and last time we discussed a case when A is Gaussian, namely that any value of A is Gaussian random element in this space. This leads, by the way, to the fact that these values are jointly Gaussian, because of linearity. And we discussed characteristics of Gaussian strong random operator and its properties. So we suppose that H is Gaussian, we agreed to use such abbreviation GSRO, Gaussian strong random operator. And in this case, it occurs that A is a continuous linear operator not only in the to the space of all random elements in H, but to the space, for example, L2 of all random elements due to the Closed-Graph theorem, and is continuous in L2 sets. L2 sets. We expect that since A is Gaussian, maybe it must be, at least in distribution, described by two objects. One is mean, another one is covariance. And last, what we did in the previous lecture was the definition of the mean of this operator. So we proved that there exists such A0, which is continuous linear operator in H, deterministic, such that for all U and X which belong to our space H, we have the following: that expectation of AU X, such scalar product, is equal the A0 U A0 U multiply on X. So one can say that formally expectation of AU is A0 U. Why I am saying formally? Because there is a theory of integration for Hilbert or Banach valued random elements, and there are different definitions, and it is now it is well defined as so-called Bochner integral from this random element. It is exactly A0U, but we don't need this deep theory. For us, it is enough that such equality holds for all U and X. Now let's speak a little bit about covariance associated with our random operator. Let me, for simplicity, denote by A with tilde the new Gaussian strong random operator defined as A minus A0. Of course, this is also a Gaussian strong random operator. Please check this. It is trivial. And for us, it is much convenient because now values of A with tilde are centered random elements in Hilbert space. So when I will study covariance, I will not write long formulas minus A0, minus A0. And now let us consider the following bilinear, multilinear form. So I will take U and V and X and Y from our Hilbert space H, and I will define the following expectation of A U X. Here is A V Y. Now let's see that AU and AV are Gaussian random elements. So one can check that this expectation is linear and continuous with respect to X and Y. This is due to that Gaussian random elements have any moments of their norm. So one can use Cauchy inequality to get continuity with respect to X and Y. So definitely there exists such an operator. Let me denote it by C. It depends on U and V, and it is acting on here is okay. So I now fix U and V and consider this expectation as a bilinear form from X and Y. It is continuous, so it is corresponding to some operator which is continuous in Hilbert space in such way. This operator naturally plays a role of covariance between AU and NV. And what we will say about it, that it is not arbitrary. Maybe you remember from the previous course on the beginning of stochastic analysis that for Gaussian random element in Hilbert space, its covariance cannot be arbitrary linear continuous operator. It must be nuclear operator. So let's check that the same happened with this. Yeah. So let's check the covariance of the operator CUV. This operator is nuclear. Let us consider EK. K is greater or equal than 1. Is also normal basis in our space H. And let us consider a sum from K equals 1 to infinity, absolute value of CUV EK. We have to check that this series converges. We have a definition of this value through the expectation, and I will write it. So it is exactly the same as the sum from K equal 1 to infinity. Here we have absolute value of expectation of A U EK. Here is A V K. Okay, absolutely. Now, since my whiteboard is too small, I will proceed with erasing. So I will put it there and put here sign less or equal. Yeah? And then I will apply Cauchy inequality. So it will be less or equal than the sum from K equal 1 to infinity square root of expectation of A U E K square. Here is square root of expectation of A U E K square. And now I will again apply Cauchy inequality to this sum. So it is less or equal than less or equal than the sum square root of sum from K equal 1 to infinity. Here is E A U K square and square root sum from K equal n to infinity E A V K square. And here we can interchange expectation and sum because of non-negativity of this random variable, and get the expectation of the norm of AU, which is finite. So it is equal exactly square root of expectation norm of AU square multiply expectation of AV square. So we proved that our covariance operator has such properties that for arbitrary orthonormal basis, the mentioned sum is finite, so it is nuclear operator. We see that Gaussian random operator still the Gaussian random vector, Gaussian random variable is described in distribution by two non-random objects which plays a role of the mean and covariance. This is about the structure. Of course, specifying the mean and covariance one can get different properties of the Gaussian strong random operator. But now we will go to the problem of the action of Gaussian strong random operator on random elements. This is the main subject of consideration of our lecture today. Action of Gaussian strong random operator on random elements. I recall you that here we have a problem, and here we have what to do at least by the following reason. We already discussed that strong random operator can have different modifications because of this infinite dimension of the space. And depending on these modifications, action on random elements can be different. Moreover, it can happen in very simple situation that even we cannot define in a usual way action of our random operator on random elements. Let me show you trivial example. Now I will consider not the random operator, Gaussian random operator, but Gaussian functional. Very well known to us because we considered this example before, and I hope you will recognize it. So let me consider Gaussian strong random functional. Random functional. In H, I will define it as follows. I will consider the orthonormal basis in H, EK is orthonormal basis. Together with this basis, I am considering the sequence K with IID standard normal values. And now I am defining the functional in our space H as follows. Defined for all u belonging to H. A of u is just a sum from k equal 1 to 50. Here is psi k u. This is a series which is converging in any sense. It is trivial to check that it is convergent in L2 sense. When you calculate the expectation of the square of the difference between two partial sums, you will get psi k square expectation, which is equal to 1, and u e k square. And different products, psi k, psi j, will disappear because of independence. Yeah? We discussed before that this series converges in square mean. But due to Kolmogorov two-series theorem, one can check that it converges with probability 1. and it can be checked that it converges in any LP, even greater than 2. Please do this as an exercise. So we have such a series, and we already discussed with you also that this mapping is not generated by the continuous linear functional in the space H, and now it is trivial because of independence and identical distribution of this psi k. One can have that sum from k equal 1 to infinity psi k square is plus infinity. So it is not psi k are not coordinates of some vector from H. It is not a continuous random function. Yes, it is strong linear functional exactly in Dorogovtsev. So now let us consider together with this random functional, consider random element in space H. I will consider the random element zeta, which is equal to sum from k equal 1 to infinity psi k over n multiplied by e. I am claiming that this is a random element in the space H. Why? It is trivial because all what we need to check is the finiteness of the sum of squares of coordinates. And really, one can check that now sum from k equal 1 to infinity psi k square over k square. This is sum, excuse me, here is k. This is sum of squares of coordinates is finite. Why? Because the expectation of this is equal exactly sum from k equal 1 to infinity 1 over k square, and it is e square or 6. Yeah. So it is finite. Hence, it is random element. Now we have two objects. We have the strong linear functional, and we have a random element in H. Let us try to discuss the action of this random functional on this random element and see what happens. So I'm substituting. Instead of u in this formula, I will substitute zeta. Formally, I will get a zeta must be equal sum from k equal 1 to infinity. Here is psi k multiplied by what? This is product u e k. Now zeta u k is equal psi k over k. Yeah? So here is again psi k over k, and finally we have this is sum from k equal 1 to infinity psi k square over k. And at least in the expectation, if we take expectation of this, we will get infinity because of harmonic series diverges, and the expectation of psi k square is equal to 1. But please again use Kolmogorov theorem about two series and check that this series diverge with probability 1. So it is equal to infinity with probability 1. So this is a bad news for us. Yeah? How we can discuss the action of Raumschen strong random on Gaussian random element. This is a very bad news, I must say, because Gaussian random element itself is a very good random element in Hilbert space. It has moments of any kind. It has even exponential moments, as we discussed in previous semester. So it is very nice random element. This is very simple, strong random function, but this action is not well defined. Yeah. So this is not this a zeta is not well defined. So maybe we have to invent some other definition of action of random Gaussian strong random operator on the random numbers. And today we will discuss this. Since we discussed it in the beginning of our lectures in this semester, that the idea to consider action of Gaussian random or strong random operators on random elements came from the theory of stochastic integration. We discussed that sometime we need to enlarge Ito theory. So maybe it is good now when we face a problem, just make a step back and try to apply machinery which we already know. Maybe we can invent something based on the previous consideration related to stochastic calculus. And it is true. So let us recall some elements of stochastic calculus which we will need today and on the next lectures when discussing action of Gaussian strong random operator on the random elements. Now, let me recall what we have. We have separate Hilbert space H, and I will suppose that I have here Gaussian white noise. So let us say that psi is a Gaussian white noise. Actually, one can distinguish the space where we have Gaussian noise and space where we are working. So to be very formal, very bureaucratic man, I have to put here zero and say that this is space. There are space H and there are space H0. Yeah, here is white noise. Here we discuss our random operators. But I think that this is formal things which is not necessary to do. Everybody can do it by okay. Now let me recall you what is it. What is it? It is exactly a strong Gaussian functional which we discussed right now. So what we have? We have a family of products psi H, when H belongs to our Hilbert space, such that psi H has a Gaussian distribution with the following parameters, and is linear, yeah, and maybe it is not necessary to put here one. is linear with respect to each. So we have such a family, and this family is called Gaussian white noise. Yeah, and as we mentioned just now, this family is not related in case of infinite dimension of H, is not related to any Gaussian random variable in H in our Hilbert space, but still we have such scalar products. It recall exactly the situation from Alice in the Wonderland, that we have no Cheshire's cat, but we have his smile. Here we have no random element, but we still have its smile. Okay. Now, what I will suppose? I will suppose further the following crucial thing, that our sigma field of the random events is generated by Xi. This is what we will suppose from now. And why it is crucial? Because if we suppose following thing, then any random variable became to be a functional from our Xi. And we remember that we have some tools to discuss functionals from Gaussian white noise. Let me recall what we discussing. So L2 integrate functionals from Xi. How one can discuss? It occurs, first of all, that they can be expanded in a series of infinitely dimensional Hermite polynomials or multilinear Hilbert-Schmidt forms from Xi. The construction is following. Firstly, let us define, as usual, Hermite polynomials. Hermite polynomials in one-dimensional case with the main coefficient equal to 1 can be defined as follows. This is -1 and power. Here is E x square. Here is d dx and E minus x squared. This is a definition of a Hermite polynomial in a one-dimensional case. The first Hermite polynomials looks like 1, x squared minus 1, and so on. Hermite polynomials have good properties. Let me mention several of them. Hn plus 1 from x is equal hnx minus hn prime x. It is derivative. Also h n prime x is equal to n h n minus 1 x. These two properties are very important for further calculations, and they lead, or this formula lead to the following expression for exponential generated function for Hermite polynomials, namely, if we consider xy minus y or 2, then is equal to the sum k equal 0 to infinity, and here is x k or k factorial Hermite polynomial h k of y. Okay, so we have such an exponential generated function for Hermite polynomials. Further, if we consider some Gaussian standard random variable, if xi1 has a standard normal distribution, then expectation of h k xi1 over square root of k factorial multiplied with hm xi1 square root of m factorial is equal to delta km. This is a Kronecker symbol of which is equal to 1 if k equal to m and 0 in opposite case. So we now have a very good orthonormal basis in the space of functionals from one standard Gaussian variable. So maybe it is understandable that when we will construct orthonormal basis in the space of functionals, from square integrated functionals from our Gaussian white noise, we will use the infinite family of such Hermite polynomials from different coordinates of our white noise, and it is true. Now let us present the main construction. Just consider AK or AN is n linear symmetric Hilbert-Schmidt form on H. Formally, AN belongs to tensor product n times H onto itself symmetric part. More detailing, AN is acting AN is acting from HN R and is linear with respect to any argument. Moreover, for arbitrary k is a more orthonormal basis have the following: the sum from k1 kn equal 1 to infinity a from ek1 ekn square is less than infinity. Yeah. One can check that this sum does not depend on the choice of the basis, and we even will say that this sum is the square of the AN norm. Yeah. This is a norm in the tensor product, or a Hilbert-Schmidt norm of this multilinear Hilbert-Schmidt form. And it is symmetric, as I call it. And symmetricity means that I can apply any permutation to the argument here without changing of its value. Yeah? This is a definition. Let me give you some example which was important for us in the previous semester. That if H is equal to, for example, 0, 1, then one can consider AN, which belong to L2, 0, 1 in n power, and AN is symmetric with respect to all coordinates. Then one can define AN from phi1, phi as a multiple integral from 0 to 1 n times. Here is H, n, T1, Tn, here phi1, T1, and so on, phi Tn, dt1, dtn. This is the example of Hilbert-Schmidt form. By the way, it will be good to prove that in this case, this exactly description of all symmetric Hilbert-Schmidt form on this space. So every symmetric Hilbert-Schmidt form can be presented in such a way with some symmetric kernel from this. Okay, so this is an example. Now let us define the weak product of the Gaussian random variables. So suppose that I fixed EK as usual orthonormal basis in H. Now I am considering coordinates of our white noise. As we said, it does not exist itself, but it has a lot of influence. EK is psi k, k is greater or equal than 1. Due to the properties of white noise, psi k is a sequence of independent standard random variables. So psi k, k is greater or equal than 1, is IID standard normal variables. Now let me define the following product: psi k1 and so on, psi kn And I put here instead of sign of multiplication, instead of dot, I put here star. And it is defined by the following procedure. Here I have a set of indices. Some of them can repeat. So let us collect all repeating items. And if we collect them, we must have something like this. Psi J1 in R1 power multiply psi Jm in Rm power. Yeah. So what I'm doing now, I just collecting the same indices. I collect and get, if it will be a usual product, then I must have such an expression where index J1 is repeating here exactly R1 times, J2 is repeating here exactly R2 times, and so on. But now I am substituting this power by Hermite polynomials of the same order. So it is equal to, by definition, HR1 psi J1, psi J1, H R2 psi J2, and so on. H RM psi J. So what we are doing, we collecting the same random variables and substituting their powers by Hermite polynomials of the same order. This is so-called weak product. It is well-known procedure in quantum physics, and we will discuss this later, the relationship between our considerations and quantum physics. So this is weak product. Okay. Now we are ready to define multilinear Hilbert-Schmidt form from our white noise psi. Let me recall that psi does not exist. So I cannot simply put it as an argument in the end. We must define what is it. And here is a definition. And here is a definition. The definition is following. This is a multiple sum k1 kn equal 1 to infinity, and here we have an ek1 ekn. It is usual, yes. And here we have the following: multiply psi k1, and here is weak product psi kn. This is a definition. We use actually natural idea. If we want to put there some element, we can use expansion with orthonormal basis of this element, put elements of the basis inside of our form, and then write coordinates. Only one difference, but very essential difference, is that we use not usual product, but weak product. This is a definition. By the way, it will be very nice to check that to give an example, maybe in A2 and equal to 2, when with the usual dots here, this series does not converge. Please give such example. So we with necessity have to do something to define the action of the multilinear Hilbert-Schmidt form on the white noise, and we did this. Yeah. Moreover, we know from the last semester that this the obtained random variables have a good properties. For example, expectation of this when n is greater than 1 is equal to 0. The second moment an is n factorial multiplied on the norm n square. The expectation of the product an xi am xi is equal to delta nm, again on the n factorial norm, and here is not norm. Okay, in this case, maybe it's better to write here b, yes, and here is a product a n b n n. In case m is equal to n. Yeah. So this multilinear Hilbert-Schmidt forms from our white noise plays a role of infinite dimensional polynomials, and now it is not very surprising. And we also discussed this in the previous semester, that we have the following abstract form of Ito-Wiener expansion. For arbitrary alpha, which belong to L2 omega fp. By the way, let me recall you that now this f is generated by xi. So alpha is square integral functional from xi, but not a function because xi doesn't exist. Yeah? Functional from xi. We have the unique expansion. This is a sum from k from n equal 0 to infinity an of xi where the expansion is unique and expectation of alpha is a0. This is a number, and expectation of alpha square is equal to the sum from k from n equals 0 to infinity n factorial norm an square. M is norm. We already studied such properties of Ito-Wiener expansion. Ito expansion. And very simple and convenient form this expansion have for so-called stochastic exponents. We will use these exponents later on very often due to its good properties. And now also let me mention if we define stochastic exponent of the element h small which belong to our space as the usual exponent of psi h minus 1/2 of norm h square, then due to the good exponential generated function for Hermite polynomials, one can have a very nice form of e-to-winner expansion for pH. Namely, it's equal to some from k from n equals 0 to infinity. Here is h. Here is 1 over n factorial h tensor power n xi. This tensor power of h is a very simple linear form. It is acting on phi1, phi(n) by the rule. This is h, phi1, h, phi2, and so on. h, pn. Okay, this is the definition of this action of this multilinear form, and we have such a good expression. Due to this, it is very good to have the expectations of the stochastic exponent with random element variable alpha, which has e-to-winner expansion mentioned before. If we consider such an expectation, due to the properties of our multilinear form, it is equal to the sum an h. This series converge, and this is analytic function on the Hilbert space H. Due to this, these elements an are the elements of power series for this analytic function. And to get this element, we have just differentiate this function n times, yeah, and take the value at 0. We will do this further, but I just mentioned. So from this point of view, this expression, this function, this is function with respect to h, uniquely define our random variable. So it looks like Fourier transform. Yeah, we have some integration with some kernel. By the way, it is also exponent like in Fourier transform. And we get some object which uniquely recover for us our initial random variable. And we will see some other good properties. So using stochastic exponent, one can define so-called Fourier-Wiener transform of our random variable alpha. Of our random variable alpha. Okay, so today we just recalled what we need for further consideration, and main idea of our lecture today was the following: that since we have to do some work in order to define action of Gaussian strong random operator on random elements, let us try to use stochastic calculus, which we developed already. Because in stochastic calculus, we at least have Ito theory, which is exempt of application of stochastic integration to random function. So maybe we can enlarge this theory using stochastic calculus in the formal situation, in the abstract situation. And to do this, I just recall the elements of stochastic calculus, which we already know, in order to be ready next time to apply it to our problem. For today, this is all. Thank you for your attention. Maybe somebody have questions or comments, please. If not, thank you again and see you next week. Bye.